Okay, final lecture, and today we have we have another change in the audience, and we have one of the co-authors.
Yeah, that's why I came.
So I think he's going to explain better than me a few points, right? We will interact later on. Okay, now let me go back to this equation, and let me present these universal potential estimates. Okay, take the fundamental solution and prove this inequality. So you trade a bit of integrability with differentiability, with Hölder continuity, and then you can easily prove that ux minus uy is controlled by weaker risk potentials times this guy. So this allows you to get a control of oscillations of the solutions via the potentials. In a certain sense, you can control the Hölder semi-norm via potentials. And Hölder semi-norm means also you are controlling fractional derivatives. Okay, at this stage, it is suitable to introduce another version of fractional spaces, because there are all kinds of fractional spaces. As I said before, Sobolev-Slobodevsky, Nikolsky, Yesov, and this is another variations, and these are called Calderon spaces. First introduced by Devore and Sharpe. So Calderon spaces can be introduced in the following way. You say that D belongs to C alpha Q if the oscillations can be controlled by a power alpha by paying a price which is now no longer a bounded function, but it's a function that can blow up sometimes. But the rate of blow up of this function is controlled by prescribing that this function is not Q. So in a certain sense, you see that this is still a non-local object, but the non-locality is reduced to a minimal status because you just use 2 points to control the thing. In some sense, M plays the role of a fractional derivative of order alpha, in some sense. So just think of it as another way of introducing, fractional derivatives or fractional differentiable functions. Okay. And then now the main idea of this universal potential estimates is that I introduced before a few estimates, one for U and one for the gradient. I introduced actually 2 estimates for the gradient. One which is slightly weaker than the other one, but let me consider now the slightly weaker one. The first one of Kilparang and Mali tells that you can bound pointwise via U via this Wolff potential. While the one I obtained with Dusar, you can use this risk potential, this Wolff potential. Let me recall you that the definition of Wolff potential at one point is integral from 0 to r mu b rho x and minus alpha p. This is 1 over p minus 1 b rho over rho. And this is the definition. Now the idea is that we want to link these 2 estimates, and we want to frame them as 2 endpoints of a general family of estimates that are not now controlling only the size of U and of U respectively, but the size of the oscillations. And this is the first universal potential estimate, which works uniformly in the whole interval 0, 1. So let me check the endpoint cases. When alpha is 0, so you do not pretend to have any control of the oscillations, what do you get? You get W1P. So you get this estimate. When alpha is equal to 1, you get essentially the other estimate. And in between you get all the sharp, let's say, estimates you might like to have.
So why do you call it universal?
Huh?
Why do you call it universal?
Because this gives you any rate of Hölder continuity, all kinds of regularity properties that you might like to have. For instance, if you want to know when U is locally Hölder continuous, then you just check that this is bound. If you want to know that this is in a fractional Sobolev space, then you prove that this guy is in L gamma, and then this gives you the Sobolev Slobodin. So any kind, so it's universal because in some sense it does not give you only the size properties in all possible spaces, but also the oscillation properties. So it catches essentially the whole thing. Of course, you might still wonder that this estimate, although being sharp when alpha is equal to 1, because it gives you this estimate, is not sharp when alpha is equal to 1, because it doesn't give the risk potential estimate, which is a bit sharper than this one. And anyway, on this I'm going to come back later, and this anyway tells you that you can pointwise bound by interpreting this thing in the way we saw via Calderon spaces, point any fractional derivative by the corresponding Wolff potential. When mu is equal to 0, this reduces to the standard estimate, and when p is equal to 2, this is always the best possible one. So this gives essentially all kinds of oscillations in terms of these potentials. So for instance, if you want to prove that U belongs to a fractional Sobolev space, you now just look at the right potential, and the right potential tells you everything. So you enlarge the family of spaces you are considering. And in particular, if you want to catch also the borderline case and when alpha is equal to 1, then you put C over alpha here, and you see that when alpha goes to 1, you will catch this other estimate, the I1 estimate, say the I1, which is before, while you lose the estimate, but in a sharp way it's 0. So this is a dual estimate. The previous estimate is completely stable, but it slightly fails to be sharp at the borderline because you cannot prescribe Wolff and risk potentials simultaneously. And so you can correct this with something which is slightly not sharp when alpha approaches to 0, but is sharp is equal to 1. And moreover, you can also use estimates via fractional operators, and you can prove this estimate actually via fractional operators. You can introduce fractional operators of this type. This is the standard fractional maximal operator, and this is the sharp fractional operator. And then we can actually prove let's say, a more universal estimate, telling you that you can bound for every alpha both the sharp maximal operator of the gradient and the sharp fractional maximal operator of U with the risk potential. This is the most general estimate that implies the other two. You can prove it that implies the other two, because you can always control D via a formula like this, and this holds for any possible function. For any locally integrable function, this formula is true, so you can control pointwise the oscillations via the sharp fractional maximal operator, and this holds for every function. Now, if you combine this estimate with this one, you get all the previous ones. Observe that C over alpha is here, and this is responsible for the appearing of this object. So you get essentially two estimates. One which is unstable at 0, one which is stable but is slightly weaker in the borderline. But combined together, these estimates, they allow you to get a complete description of all kinds of regularity in terms of potentials. And this is essentially what I wanted to tell, but from the fact that we also have an estimate for the gradient. And this estimate holds until the best possible exponent, which is provided for the gradient. So you know that for the p-Laplacean equation, that the gradient is intercontinuous up to a certain exponent. So we have a universal estimate that works exactly up to that exponent, and in addition, it gets you the estimate that you might like.
This exponent is unknown, right?
Unknown, yeah.
Yeah. But it's universal.
I mean, you can always find a lower bound which is independent of the solution. The optimal lower bound is unknown. It is conjectured always to be 1/3, because then when p goes to plus infinity, then you go
you go
to the infinity Laplacian, and then there is 1/3 which is a bound from below. Yeah. So essentially. But this is apparently a very ugly. Yeah. So essentially, we now have a complete pictures of all type of regularity via potentials. We have zero order regularity, where U is bounded by W1P. Let's say this is C0 or C0 gamma for small gamma. Then we have C0 gamma for every possible gamma, and then you have a fractional potential. Then we have the Lipschitz regularity, which is C01, which can be controlled either with this or with this one. And then we have the maximal regularity, which is C01 alpha M, the maximal regularity, and this can be still controlled with the Wolff potentials. So all in all, you have universal estimates bound to describe the regularity of solutions via potentials in all possible spaces. So Hölder spaces, size properties, and so forth. For instance, this tells you immediately, if you want to know that D is in a certain higher fractional software space, then you say that this guy is in L gamma, and this will be in W alpha gamma, provided you prescribe when this guy is in L gamma. So essentially, this is a complete reduction of the theory. And now we pass to the last section, which is non-local potential theory. So Yannick will correct me if I make mistakes.
Yeah.
Right?
Yeah.
Yeah, sure, absolutely. Okay, so that's the fractional Laplacian, isn't it? It seems so. First version, fractional Laplacian. Then we pass to a nonlinear fractional version. Actually, to a linear fractional version, but with measurable coefficients. What's the difference? Here you see the kernel n plus 2 alpha. Here you see another kernel which blows up as n plus 2 alpha, but it's not exactly that one. So in particular, a potential very bad and measurable dependence on coefficients can be hidden here, and this makes this operator completely different from the other one. Because essentially higher regularity is forbidden by the fact that if you want to get higher regularity, you unavoidably run into a differentiation under the sign of integral, and this is not differentiable anymore. So this essentially, it's the same difference that you get from this operator to the previous one is the same difference that you get from the Poisson equation to an equation with measurable and bounded and elliptic coefficients, which is this one. But then we want to go to the nonlinear case, and in the nonlinear case, you can just make a composition of this difference with a function that preserves its ellipticity properties in terms of monotonicity and boundless. While the kernel, it's still the same one before. So you get a nonlinear equation, and the nonlinearity is the fact that now the difference depends in a nonlinear way, in a nonlinear yet monotone way, because you have to keep the ellipticity going on, the monotonicity going on, and still you have bounded and measurable coefficients. Because the kernel is the same one as before, as in the previous slide. So essentially, now you are passing to an equation with measurable coefficients, but it's non-linear, but it's just monotone. And the last variation, when we approach the so-called non-local or fractional p-Laplacean operator, then we go to solutions that are in W alpha p, because I forgot to say that you look for energy solutions, and being an energy solution in that setting means being in alpha, W alpha 2. Now we go into W alpha p, and I will always assume that p is larger or equal than 2 for simplicity. And then I get the same monotone object, and now with a p growth, and the blow up that behaves accordingly. Example. This one. And this comes as the Euler-Lagrange equation when the right-hand side is 0 from a function like this. Oh, sorry, I should have put b here. So essentially, you are essentially when the kernel is really n, when the kernel is really this one, and p plus alpha, you are minimizing the Gallardo p fractional semi-norm. So this fractional is particularly natural because it comes from a variational setting. You minimize the so-called p fractional Gallardo semi-norm, and then you come up with this equation where the right-hand side is equal to 0, and then you eventually want to put a beta. Then, okay, these are the kinds of operators I'm going to deal with today. So we started from the classical fractional Laplacian, then you keep linearity, but you put measurable coefficients. You don't keep linearity, you put measurable coefficients, and you keep monotone objects, and then you go to p growth, keeping everything together. Because at this stage, you see, once again, we put measurable coefficients here, and then this tells you what is the right energy. Let's say the energy space is established by these inequalities, and then the kind of growth that couples with these inequalities is established by this monotonicity. Monotonicity also keeps the ellipticity. Let's say the right ellipticity notion in this setting. Okay, and now today I would like to present a few analogs of the nonlinear potential theory that are known for these operators. Okay, basic regularity improvements, and this is a joint work with Yannick and Theorem Kuusi, and Theorem is really one central figure in this p-fractional nonlinear stuff, because it's working really a lot on this, having very nice results. Okay, what is the most basic result known for equations of this type? Take an equation which is square monotone, that has measurable coefficients, and the right-hand side is a bit better than L2 plus delta. What can you say about solutions? They are a bit better. In particular, this is non-trivial already when f is equal to 0. This is the so-called Myers estimate. So you get, although coefficients are measurable, you get an improvement, a microscopical improvement on integrability. Let's say you switch from W12 solutions to W12 plus delta solution. This delta is universal and only depends on the eigenvalues and on the ellipticity. It does not depend neither on the operator nor on the solution you're considering. Essentially, for the linear case, this is the famous theorem of Myers. Then this was obtained by Elkat and Myers with the initially unstable proof, and then it was fixed by Gehring and Nonlinear in the local setting. This is from the 70s. What's the modern proof of this? It's going via so-called Gehring-Gehring lemma. It's variations of the Gehring's lemma. So, what is the original Gehring's lemma? Just forget about G is 0. So if you get something which satisfies a reverse inequality, let's say from P to Q and Q is less than P, then you are a bit better, because there's a self-rebalancing procedure that forbids the function to grow too much in some sense at a P level. So the idea is that you start from P, but since you can control by an average which is smaller than P, then you have to be a bit better. A better way to see this is that you know that what is an LP mean? If this is a function, then L infinity catches up this. An LP mean measures the mean values in this way. And when P goes to plus infinity, you approach LP. And LQ measures still the mean of all values, but in a different way. So it gives you a worse thing. So yeah, the self-improvement is exactly this. How does this apply to the previous theorem? It applies as follows. This is a standard fact. That's the famous Caccioppoli type inequality that just comes from basic testing of the equation. You can control du by u. And this holds for any solution of the equations I told you before. This is really not difficult. You just test the equation with the simplest possible function that is a cutoff eta squared by u, and then you use Young's inequality, and that's what you come up with. Okay, once you know this, you know that if this is satisfied for every ball, then you get an embedding. How do you prove this? It's very simple. du squared can be controlled by u. Now you apply Sobolev embedding, and then you get a reverse inequality. Once you have a reverse inequality, you apply Gehring's lemma before, and then you go from 2 to 2 plus something. And this something at this stage depends on the constant implied here. Since this constant is universal, then this is universal as well. Okay, that's the basic feature. Can you get more? The answer is no if coefficients are just measurable. In particular, this is how, in a pointwise setting, the oscillations of coefficients are linked to the oscillations of the solution. In a pointwise setting. In a pointwise setting, you know that if you want to get that the gradient is not only integrable, but if you want to get a control of the oscillations of the gradient, then you have to get a control of the oscillations of the coefficients, because the two things are linked at this stage and are linked in a pointwise setting. In particular, you know that if you want to get that u is Hölder, is continuous, then a of x must be infinity continuous. If you want to get that the gradient is C0 sigma, then a of x must be C0 sigma, and this is Hölder theory. So the second line is the famous Hölder theory. And if you want to get that the gradient is in a Nikolsky or a fractional space, then the coefficient must be in a Nikolsky space. But if the coefficients are nowhere, then the gradient is nowhere. So there's no control on the oscillations. Example, just take the one-dimensional example. This means that this is a solution. The gradient of this is 1 over a. They can be far from 0 and infinity, it can be whatever. So in the local setting, since the equation is local, coefficients act so locally and strong on the solutions that they forbid any kind of improvement if they are not very good. So a surprising feature now of non-local problems.
For divergence equations. For non-divergence, it's much better.
It's much better, but not really, because
yes, if you have like Aij, Dij, if Aij is C alpha, and Dij is C alpha.
No, so because you have to for divergence for non-divergence operator you always do a step beyond. And once you do the step beyond, then the phenomenon is the same. Then the phenomenon is the same.
So what do you mean by step beyond?
Step beyond, you see, a of x is linked to be here.
No, exactly.
But the sharp improvement is the same at that stage. You do just +1.
Yeah,
but not
you gain
1 plus
derivatives.
delta.
You gain derivatives.
You gain one derivative, but not more from the coefficient.
No, sure.
That's what I meant. Okay, and now let me consider an integral differential operator of this type, where this is the usual form I told you at the beginning. So this depends on the kernel. The kernel is just assumed to have this ellipticity and bounds. So essentially we are considering the analog of linear equations with measurable coefficients. And for these equations we know that the gradient is a bit more integrable in the local case, but there's no additional control on the oscillations of the gradient. Okay, in the classical way of doing of, let's say, refining in the non-local setting what is possible to and what is known of the local thing, then the first thing you want to improve is that you start from an energy solution which is in W alpha 2, and then you want to improve in 2 plus delta. This is the analog you want to do. That's what you do for local equations. And that's the analog of the Myers property. Let me just recall you that this is the usual alpha reality. So essentially you want to bound this, and essentially this is the natural thing you would like to ask for. And this was in fact done by Bass and Ren, who proved that this alpha gradient is in L2 plus delta. Then there's a theorem of Stein saying that this is in L2 plus delta, that this implies W alpha 2 plus delta. Nothing more than that, but this is the thing. But what we proved, surprisingly, with Tomo and with Yannick, is that you also improved the other scale. And the other scale, it's the leading scale, because then by embedding gives you the other one. Particularly, you know that if a function u belongs to w plus delta 2, then this will belong to w alpha 2 plus delta 1 from some delta 1. So there's an additional improvement of differentiability that is completely, it's a completely, genuinely non-local effect. So you cannot only, and result is false in the local case. So this is one of the very few, you can count on the fingers on one hand, of the very few non-local results which are purely non-local, in the sense that this is not true for the local case. And the failure of this result in the local case I showed you with the counterexample before. Okay, and now let me give you the statement. In the classical case, the most general one of the most general equations you can consider is this one. Therefore, we can consider also these equations with the right-hand side, and we can easily compute what are the optimal assumptions on the right-hand side by considering the model case of the fractional Laplacian. In the fractional Laplacian, you can do computations via Fourier transform. So if you do Fourier transform, you make a bit of heuristics, and so you know that by Calderon-Sigmund theory, the 2 alpha derivatives are in LP, then U is in 2 alpha P. Now you want to trade differentiability, since you are interested not in alpha plus delta, so almost alpha, you don't need to have 2 alpha. So you want to trade this 2 alpha in alpha, so lowering the differentiability exponent and increasing the integrability 1. This you can do along the Gallardo interpolation plane. And so this embeds here with this inequality. So all in all, you can find that if you want to get a solution that is in W alpha 2, then it is sufficient to have this for some exactly here. And then if you want to have alpha plus something, then you have to add something here. So this is the minimal assumption if you want to get some regularity on measurable coefficients. And that's effectively what we prove under these optimal assumptions. And this is essentially the new phenomenon we have discovered in this paper. This is really a new phenomenon in the non-local setting, because it's a phenomenon that doesn't appear there. So the heuristic explanation of this phenomenon is that on one side, you have that the coefficients, since this is a non-local problem, then the coefficients, it is true that the coefficients are influencing the solution, but there's also an averaging effect that makes this influence weaker, while this averaging effect happens with a singular kernel, and the fact that you are rebalancing these singularities gives you additional differentiability. This is essentially what the effect we exploited in the proof. Essentially, what we realized what is the real analog of the Gehring's lemma for fractional problems. And in fact, after a couple of years, then there's another proof of Shikora, which is completely different. Actually, our proof also works for non-local p-Laplacian, because once you know how to deal with reverse inequalities, then p or 2 is not very important. Then Shikora made another proof using nonlinear commutators, that also gives the analog of this result of Ibanez-Bourdon. This does not only give that you can improve from alpha to alpha plus delta, but also if you start from a very weak solution, so something which is not in the natural energy space, both with respect to the integrability and the differentiability, then you can improve in this. Actually, we also expected something. I remember when we wrote the paper that we can. Okay, the approach of this Shikora is very interesting. It goes via very refined estimates via commutators, and I think it's really worth looking at paper. And the difference between the two papers is that actually our Shikora's proof is faster because it incorporates a lot of information using commutators, but it only works for equations, while our approach is via reverse Hölder inequalities and can also exploit it directly for minimizers without differentiating the equation. That's the usual duality. There are certain things that can be done only for solutions if you have a solution in your hand, while there are other things that can be done directly for minimizers, also in those cases where the Hölder-Lagrange equation associated to the functional is not available because the functional is not regular enough. Okay, let me tell about this fractional approach to Gehring's lemma. And the fractional approach to Gehring's lemma, let me recall the approach. The approach is the theorem I told you before. Any function satisfying a reverse Caccioppoli type inequality like this, then has a higher power. Has a first derivative which is integrable with a higher power than the one given by the fact that it belongs to the natural Lagrange space. Actually, what we prove with the Tuomo Yannick is that if you get a function W alpha that satisfies this reverse inequality, then this has this property. Okay, what is this inequality about? Just read the first line, and you will see that this is completely analog. This is completely analogous to the previous one. In the previous one, you have first derivative. You have here alpha derivatives. Just look at the scaling. This is, in some sense, an alpha type derivative. Here you get 1 over r squared. Here you get the right scaling that compensates this one. So up to now, the two inequalities are completely similar. And in fact, this is really the important part in the fact, because this is the part that analyzes things around the diagonal. I mean, these non-local problems, many things can be done for non-local problems, essentially because the analysis of regularity of non-local problems is a delicate interplay between what happens in the real bulk part, that is the things around the diagonal, and what happens outside and far from the diagonal. So this interplay, actually what is really important is what happens around the diagonal. And what happens around the diagonal really makes the game going on. And now the difference is that we have an additional part, which is a tail part, that takes into account the long-range interactions, let's say the behavior of the solution of the problem when you're far from the diagonal. And this can be rewritten in the following way. But then the abstract theorem is that any function satisfying this inequality then is more differentiable. And of course, solutions are satisfying these inequalities. If you take a solution, then the right Caccioppoli type inequality can be written in the following way. And once you know this, now the point is how to prove this. Now, if you want to prove this, then the idea is the following one. Okay, if you are in W12, what does this mean? It means that the gradient square is finite when you test against a locally finite measure, triviality. Right? Now, what it does mean that the function is in W alpha 2? This means that this object, which is dimensionally the analog of a gradient, is finite, but when you test it around a singular measure. So there should be a microscopical information of a logarithmic type, which is hidden here. And now whoever knows the first real proof of Gehling's lemma knows that the first proof of Gehling's lemma was obtained by first getting a logarithmic type improvement, and then iterating this logarithmic type improvement, then you get a power type improvement. So the idea is that whenever you get a logarithmic improvement, there should be a power type improvement. And now you see a log, because this misses of being integrable by a log. But if the two things coupled together are integrable, this means that if a log is missing here, a log should be here. And iterating a log, there should be a power there. So this is the very obscure heuristic argument. Actually, this heuristic argument is true because of the following. Now, we introduce the idea of dual pairs, which is a triviality. I mean, if you write down in the following way. Okay, we take now the difference quotient, but not the usual difference quotient. We improve a bit. Okay? And now we take this measure. Now, surprise, surprise, this measure is locally finite. Now, this improved difference quotient is finite again against a locally finite measure. So there should be an effect like in the local case. So if you're able to prove something better for this, you're done. Why? Because now we translate the Caccioppoli type inequality in terms of, okay, what we do is the following thing. We have a Caccioppoli type inequality in Rn. For U. Okay? Now we go back to capital U and mu, and we lift this Caccioppoli inequality in a mu inequality, which is in Rn times n. Then we prove a local version for dual pairs of Gehring's lemma. And then we discover that after you improve in R to n the integrability of U, then an improvement of integrability of capital U gives an improvement of differentiability of U, because it incorporates more information about differentiability. And this is exactly what we prove. Why? Because U plus delta in the mu, it's exactly n plus 2 plus delta, this guy. This guy, that's it. So the idea is the following. So you get U against, you get the difference quotients of U which are finite against an infinite measure. So by duality, you get a better difference quotient which is finite against a finite measure. So you keep and that's the passage of information. The passage from integrability to differentiability. So that's the trade-off, right? And once you know this, you can go back to the original function U, getting both differentiability and this. Okay, the proof takes around 60 pages of heavy dyadic decompositions, right? I mean, it's something which is horrible. This was a horrible period. This was really a horrible period of our lives, right? Checking all these dyadic decompositions with personal lives destroyed, literally. Okay. And in fact, what we are able to prove is the following version. The Caccioppoli inequality I showed you before translates into the following reverse type inequality. Capital U is the one I told you, and then it satisfies the following reverse inequality. What are these guys? These are products of balls. And now, if this is true, then you get an improvement as in the usual case. So formally speaking, this is the usual reverse inequality. You see, you get, this is the tail that takes into account the long-term interactions. This looks as a reverse inequality and gets an improvement. Now you might like to say that now this is close to the Gehring's lemma, because there are versions of Gehring's lemma in a more abstract context, and with versions that tells that if you have a doubling measure, and if you have a reverse inequality like this for every pole, and this is a general doubling measure, say Q, P, and P, then F belongs to LP plus delta with respect to the measure, and this looks like this. Actually, it is not. Why? Because now you are in R to the 2n. So if you would like to apply these versions of Gehring's lemma, you have to take into account all the possible balls. All possible balls means that these balls must be here, must be here, must be here. But surprise, surprise, the real bad thing is that here only the diagonal balls are considered. So you have a complete lack of information on the other balls. And the whole game is now to to see that, that far from the diagonal, these balls can be controlled by the diagonal balls because the whole game happens around the diagonal. So this is a very, let's say, I would say, technically speaking, this is probably, I mean, I should not say because I'm one of the authors, but I would regard this as outstandingly technically difficult. But the idea is that the one of dual pairs. Okay, finally, what about the regularity of solutions? In the last 10 or 15 minutes, I can talk about a bit the regularity of solutions, about fractional p-Laplacean. And here I would like to mention this is basic work of Theorem Kuusi, Agnese Di Castro, and Giampiero Palatucci. Tuomo is really doing a lot with p-fractional problems. Palatucci is nowadays extremely well known for this incredibly quoted survey paper he wrote together with Yates and Baldinucci. But he has also very nice analysis papers on this fractional problem. So he's a fractional guy, right? We can say he's a fractional guy. I will consider the case p larger or equal than 2. And I will consider non-local Dirichlet problems, and as it is common in these cases, here, since the problem is non-local, there's a problem in defining the boundary values, and therefore you have to prescribe the boundary values in all over the remaining part of the domain. Anyway, we will consider solutions of this type. And let me briefly give you a definition. We consider the tail of a function d as this quantity that you already saw appearing in the previous slide. So essentially, this is a sort of non-local potential that takes into account the long-term interactions of these things. And usually G and all problems are considered in W alpha p, but you can also restrict to W alpha p lock, provided you are in this tail space. This tail space is nothing but, I mean, the minimal condition making things work. And there's nothing deep, it's just a bit. Okay, then we have two theorems. And the first one is sup-bound, that tells you that exactly, you see, you get the same sup-bound plus the tail term, and this gives you a flavor of the kind of problems you're encountering. This works for solutions to the p-Laplacean equations. This extends previous basic work that was done by people like Raffaelli and Silvestre and Kassmann, who dealt with the case p equals to 2, and essentially this is the nonlinear case under optimal assumptions. Together with this, and this is essentially the De Giorgi's theory in the non-local version for p-cross conditions. This was first done by Raffaelli and Silvestre for the fractional p-Laplacean, then by Kassmann, and then now there is this paper. Kassmann for the case p equals to 2 under additional assumptions. And again, there's also the oscillation bound, which is a Hölder continuous bound, because you see that on B rho, this is decaying like a rho to the beta, and the estimate is the usual one, but for the appearance of this tail term that encodes the various long-term interactions, long-range interactions. They also have a related type inequality that allows for some solutions, and then there's a couple of recent papers by Imply, Palatucci, and of course Theorem Kuusi, who is going to be here and next week, and he's going to talk about exactly this. And these are papers that are bound to give a general view of nonlinear potential theory in a more abstract setting for these non-local problems. And these two results were prior to the last part of these lectures, that are potential estimates in the non-local case, and this is again work with Yannick. Now I'm talking about the p-Laplacean case, and with right-hand side equals to a measure. Okay, please do not read the slide. The slide is there just to tell you that the solutions I'm going to consider are the usual solutions obtained by limiting approximation. The limiting approximation this time must be prescribed both with the measures and the right-hand side together with the tails term. Okay, everything fits. These are the minimal conditions for which everything can be redone and well defined in terms of definitions. Now we go to the results, and we take now the p-Laplacean operator, the non-local p-Laplacean operator equals to a measure, and we have essentially two results. And the first result is the analog of this Kilpelainen-Mani theorem. So we are able to pointwise bound U by the Wolff potential W alpha P. And you see, while in the local case we had W1P, here we have W alpha P, plus the local term that you saw before, plus the tail term that must be there to take into account the non-local part. In particular, we have an analog of the fine property of the potential of the solution if the potential is finite. If the suitable, Wolff potential, the natural Wolff potential is finite, then this is a Lebesgue point and everything works. So you can give sense to the left-hand side, and this is the precise representative. Otherwise, this is plus infinity, and who cares about everything? That's the point. So this, essentially, the two things must be put together, because essentially this line allows to tell you that this estimate works for all those points that are really meaningful. Because either the right-hand side is plus infinity, and then who cares, or it's finite, and then this is the Lebesgue point. Now you observe the differences with the local case. With the local case, you have W1P, where this is the usual P potential, and this is the alpha P potential. So this is the analog of the potential estimate. And finally, we have also the continuity result that tells you that if the Wolff potential goes to zero uniformly, then U is continuous. In particular, this implies all the possible kinds of corollaries on solutions. Essentially, you have either the fractional Laplacian, even a non-local operator with measurable coefficients, or a fractional p-Laplacian, and this is the most possible general condition that allows you to get that the solutions are continuous. And once again, this parallels the one that we saw before in the local case. Should I say that this is finally the end? This is redemption, right? You young guys. Okay, that's all. I think the program starts.
The program of the week is over. So
it's over, right?